All right, good morning, everyone. Good to see you all. Hope you have had a good week. This is Friday. Happy Friday to all of you. And you have hopefully by now seen all of your classes and how things would look like for this week. I want to get started. It's almost 10 past 10. And I have put up an agenda on what we will be doing today. I would like to continue discussing Turing machines, which is what we have started this week, and I want to continue with that one. But there are a couple items before that that I would like us to take care of. And I want to begin by just doing something like what we did last time to just warm up and see where everyone is and how they are doing. So I'm going to have a few questions, and we're going to use the group chat section for having to do with this one. No, we are not having midterm today. No, that's not what I'm saying. And I want to talk about what that one is. But let's not worry too much about what is there. And I want to know if everyone had breakfast already. Did you have your breakfast? So I'm going to ask one or two questions, and so you will be responding. So the first question is, did you have your breakfast today? And possible answers are yes, not yet, or I'm having it now. And I want people to get a chance to answer to this one. And we'll call that one question one. And I'm going to ask a follow-up question for that one, and I don't want people to get confused which one is. So right now we are answering the question, did you have your breakfast yet? Yes, no, or I'm having now. There are some of you who might be having your breakfast while you attend lecture, which is perfectly okay. I'm going to wait another 10 seconds or so for people to answer to this question. And then the next one is normally, so that's pre-COVID-19, what meal is the most important for you? The answer would be breakfast, lunch, dinner. Okay, looks like dinner. Okay. So there is a good, it's almost unanimously dinner, very interesting. Brunch is also an option. Keep answering that one. How did your response to question 2 this week? There is potentially some change. Some people might have started to work late or do some other change. I just want to know the same, or if there is a change, you let me know. Okay. 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 So for those of you joined late, we are talking about what meal is the most important for us normally between breakfast, lunch, and dinner, and how things have changed this week. That's question 3. Question 2 was just which meal is the most important for you. All right, I'm going to stop questioning except for one last question. Question number 4, this one is going to be, what is your favorite color? Okay. All right, we've got all kinds of colors. Green and red seem to dominate. Pink, I would expect them to show up. Oh, there is purple. Oh, you're not supposed to say purple. Okay, no crimson. Okay, I'm not trying to bias anybody. All right, I think we did part 1 of our agenda. If you haven't participated in the discussion, go ahead and do, though. That was the warm-up part. Midterm 2 is what I want to talk about, what I have decided. I've asked you for your inputs in the survey, and I did listen to you. I did get a good number of you replying one way or another. And the discussion was, or the question was, whether we should have this one online or take home. And after weighing what you've said, and after I've seen how things are, what resources we need, I have decided to make this one take home. And I'll explain in a second what that one means. Homework 6 is out. I did send a note yesterday. Some of you might have already seen it on Osbol, and I want to talk about that one a little bit. We spend a couple, 2-3 minutes on these 2 items, and then we get started without lecture. That's the agenda for today. We are not having midterm 2 today. No, no, no. So let me go to the next slide and talk about these 2 items, and then we will start with our discussion for today's lecture. So here is how I have put together the kind of homework and general look or at a glance for how the weeks look ahead now, including the one that we just finished, to see towards our final week and the end of the semester. And so we just finished this week now, and today has homework 6 gone out. I'll tell you a little bit about that one in my next slide, and where this is going to be due next Friday, a week from now, and this is going to be very similar to how things have been before the spring break and before how things have changed now in terms of being online. I'll tell you the nature of the problems in a second, and you have got a full week to work on it. The second midterm, I decided to have it on April 10th. That will be 2 weeks, exactly 2 weeks from now. And so for that reason, we will not have the 7th homework until after we are done with midterm 2. The reason I made it to be take home is because there isn't a good support for the kind of thing I was thinking about doing it online. And plus it aligned better in terms of the practice I would like you to have as we go ahead and finish them, learn more things and things like that. So think of it as something that is an extension, more of the nature of the homeworks type, but with fewer questions and different nature of question. And for that one, you will get a 24-hour period instead of having an entire week like what you've done in a homework. This will have a different flavor, and it will be a little bit more focused in terms of the I'm thinking about 5 problems in it. 2 of them will be around the topics we are talking about now, and maybe another 2 of them would look back a little bit on other things. But it will be creative. I'm thinking about how it will be different from homework, and this based on my assessment of how things are to be done if it was going to be online, and the kind of feedback I got from most of you. This is the best compromise I have. And so that will be the week where you will have your second midterm, and then we have 2 more homeworks, and that will be 7 and 8, and the times they will be out and the times they will be in is indicated there. So the last 2 weeks or 3 weeks will be where the 2 homeworks will go out and come in. I have also, at the same time as the midterm 2, thought about how the final would be. And until yesterday or so, my inclination was to have it online. And for a very similar reason, I prefer, and I would probably ask you separately to weigh in on that one, plus the stress you probably may have with other courses or during finals week. I would like the finals also to be a take-home. But that will be even a different nature than what the second midterm would be. And you will have maybe a longer window than what the second midterm will have. The second midterm will have a 24-hour period. It will be out that Friday, and then it will be in either the very end of that Friday or the Saturday morning, 24-hour period. Whereas for the final, I might make it 48 hours or 72 hours. But I am going to be creatively thinking about how the finals would be also done. And I would like to avoid as much as I can an online exam. It did not work out the way I had thought it would in terms of having both to assess you and give you a chance to learn from it. And so this is how the post-spring, the 6 weeks we have look like. And one of the things I would like to know is how many of you have got how many finals in the finals week. I have put a date for having a due date for the finals. And that will be the day that my WSU or the Pullman course scheduling people would have had us 317's final, and that would have been on a Thursday, 8 to 10 a.m. And I would like to use that one as a time when you would have your report in, or what the exam that you will do, it will be due during that period. And if you need to, finish up something and so on, you'll have at least a dedicated 2 hour that's conflict free from other finals that you may have, where you will turn it in. And so this is how I'm thinking, for especially about the final. I think if there is any reason why I would have to make any adjustments, I'll put a survey and have 1 or 2 very simple questions where you will participate. That's what I am thinking of doing. But this is how we look. And we look good in terms of the weeks that are left, the topics that were left for us, and the 3 assignments spread, to me, looks a good one. And my hope is that midterm 2 is falling at a convenient time for many of you. In terms of topic coverage and layout of assignments timing, it works out well from my perspective, but I hope it is going to be something that you will also have some advantage compared to other courses as you do with this one. So that was my item 1 in the agenda. The other item is to tell you about homework 6. If you haven't seen it, take a look at it today. To be very honest, I had actually put it on Osbol yesterday night, the moment I sent you the notes, and it has got 6 problems, just like it has been so far. The first 3 problems are problems that were on topics covered before spring break, and what James and I noticed in how you have done on homework 5, which you haven't heard back from us yet, where people, not necessarily everyone, has got a good mastery of topics. And so the first 2 problems try to address that. I think there is a good portion of the class that would need some more kind of practice in converting context-free grammars to push-down automata. And so that will be one of the problems. The first problem will address that one. The second problem will address a conversion of a context-free grammar into Chomsky normal form. On that one also, I think getting another problem to work on will be good. You've had variations of either of these 2 problems in homework 5, but so you get another chance to practice is what it means. Problem 3 is on applying the pumping lemma to show if a given language is not context-free, so you get 1 more chance to do that. Problem 4 is on a topic I covered right before we went out for spring break. In fact, that was a Zoom class we had on a Friday, March 13, and that was to do with minimizing the number of states in a DFA. And so I ran through an example, and so here you'll get a chance to work on a problem that tries to apply that algorithm. Okay, so problems 1 to 4 were pre-Turing machines. Problems 5 and 6 are Turing machine. One of them would ask you to do more like an informal description, like the ones we have seen in our last lecture, and one problem which would ask you to go even deeper and draw a state diagram. And that's not going to be a hugely complex Turing machine, so that you will have a reasonable size of state diagrams to draw. This is what the problems look like. You will enjoy them, I'm sure, and they're good ones, and they are due on a Friday. I have kept my word. Friday is today, it is out 8 a.m. officially on Osbol, but when you turn it in, you get the entire Friday up to midnight. But don't wait until the very last minute, submit it. This will happen on Osbol. You will submit a PDF file. You have a choice. You can either handwrite your solution like what you would have done normally, and then scan it or take a picture of it and submit on Osbol. Or if you prefer, you can type up your solution and generate a PDF, including the ones that would require you to draw diagrams. Whatever is easier for you, go ahead and do that. I'm going to share a video that I have seen a professor make on having to turn a paper-written, a handwritten thing into a PDF in a proper way, or in a better way than what your cell phones would do. I'll put that video link on Osbol. If you find it useful, use it. If not, then just do what you want to do, what you are convenient of doing. Handwrite, scan, or take a picture, upload on Osbol, or type up, get a PDF and upload on Osbol. And you can upload or submit your solution anytime, as soon as you're ready, but the deadline is Friday the 3rd by midnight. And so this is how things look like here, and I'm going to get started with today's topic. If you have any questions, use the chat room, and I'm going to keep my eye on it to ask question, or you could raise your hand on the participants one, and I'll also keep an eye on that one. Before I get started with today's topic, is there anybody who has got any question? You can also unmute yourself and speak up.
I have a question on homework 6.
Sure.
So problems 1, 2, and 3, those were things that we also did on homework 5, right?
Yes.
So is there a possibility of us getting the homework 5 solutions or feedback on our homework 5 so that we know whether or not we did the right thing?
No, absolute perfect sense. There will be both of them. I will post solution as well as feedback on them, hopefully before Monday. The reason, the solutions are ready and we could post them, but you don't have feedback, so it will not make a lot of sense. And the reason that you didn't get feedback is because James is not done correct, grading every single ones. And then I have probably explained this one before. It takes time, and especially with other things, with the adjustments we're making, it's not ready. He's more than half away, and so I'll probably lend a hand and make him finish it. But before Monday, you can be sure that you will get both the feedback, the corrections on OSBL, and how you've done, and then your solutions. That brings me to think about what you would do generally, not just you, but the rest of you, in terms of solutions that you haven't picked up from me. You got feedback, for example, on homework 1, 2, 3, 4, and if you want to review things for, in preparation for the final, or the second midterm would probably not require too much of that one, but for the finals you may. I don't know what the best way is for me to get back to you. I have them in my office. I don't go to office anymore. Nobody does. And so if there is anybody who has, very desperate need for getting them, I will probably stop in one day and then scan and send you or something like that. But I would trust that you will either have something that you can recollect other than homework 5. But for the past ones, if you really need, then we will try to find a way, if you have not collected them when I bring them to class. But homework 5, you will get feedback and solutions for the homework. Those solutions would probably be the more useful ones for doing problems 1, 2, 3. Any other questions? Okay. Is everybody up and following me? It's very hard to tell, so I don't know what question I can ask. Okay, yes, just yes is good. Is everybody following me? Am I loud enough? Yes, okay. All right, I appreciate the response. I really appreciate how you are handling this and how you are being responsive to the class and your participation. So let's get going. We are going to be talking about, we're talking about Turing machines, and we have seen them as general purpose models for computation. And today we are going to see what changed to the basic definition we have given to Turing machine in the discussions we have had so far, what they would bring about. And these things are called variations around the definition of the model itself. So the word robust is what we will be using now, and you probably have some connection with that word. In fact, some of you I know have interest in things around machine learning or data science. For example, these days people talk about having machine learning algorithms that's robust. That means if your data is corrupted or something has happened to it, you can withstand it. Or if you are an engineering type of student, then you have the model, and so it will withstand. Or you could even be more of a social science person, or have a political discourse or discussion, and things have come in different ways. But that idea you had, it kind of persisted because it was resilient to these changes that were coming to them. And so in that sense, Turing machines are robust, and they are not the only ones. Their little cousins, finite automata and PDAs, to a degree, were robust. For example, you may very much remember when we said we are going to introduce nondeterminism. Finite automata were resilient to that, robust to that, because they didn't change in power. They were able to, the deterministic finite automata were able to recognize the same class of language non-deterministic finite automata would do. And similar things could be said about PDAs too. But this robustness to change even more so is pronounced when it comes to Turing machines. And that's the subject for today's discussion. So I'm going to start with a very, very, very simple one, a very simple variation we can make to the definition of a Turing machine and see if it is going to be the same or not. By the way, when I say the same now, what I mean is, has it been empowered to generate even more than what it used to do before? If it is recognizing the same class of language with and without that change, then that means they are equivalent, and that's what the robustness here would come. So one change one could make would be to say, okay, we had the Turing machine, it had the control, it had a tape, and it had a tape head, but we required it in its mode of operation in how things were done for the tape head to go to the left and to the right. So and that was how we augmented, for example, in terms of defining what a configuration is, and we see the head of the tape will move to the left or to the right after it has read an input as a consequence of its action with it. And it was required to do one of these two. That was the definition. And some might have thought, and I remember, I think in the discussion, somebody asking, can it not do anything? Could a Turing machine, for example, not read an input like what we have seen with the finite automata? And so it's a very reasonable thing to say. What change would it make if the tape was allowed to stay put and not just move left and right? And so then the idea then, the argument we'll make from now on, whatever change we will make, is if it's going to make a difference or not, is to say, would that variation that I am causing now can be done when I have the standard definition? Can it simulate it? Can it be made to accomplish exactly the same thing as with this variation would do? And for this particular one, the answer is yes. And I probably would relate a story, and very quick one, for that matter, to show you what this one is. It's a one-line proof for this simulation, but I want to tell you a story about somebody who went around and learned a new language, and I'll call that language Esperanto for the purpose of this discussion. The story goes by having to actually an actual language, but this person says, I have learned enough, and then there were a handful of them, and then he tells this other person that he's able to converse with that language without any problem if a native speaker of that language would come. And so he gave him the list of words he knows about this language, and this other person was kind of surprised by the claim that this few relatively dozen words would enable him to speak and communicate with this other person who speaks the language in a native way, and he challenged him. And so he asked him, suppose this native speaker of that language would come to your office, and I see in the list of words you have, you know how to say come. And let's say that person has come to your office and you get tired of them after a few conversations and you want them to leave. What would you say to them? I don't see a word for that one. And this person who claimed that that language was enough said, I have a solution for that one. If I wanted them to leave, then I would first go out of my own office and then say, come again, that same word, and that person would leave, and then I have achieved. This is basically what is happening with this Turing machine that is going to simulate what a stay would do if all the original machine has to do, or it was required to do, a left and a right move. And if a stay is going to be achieved, then this old Turing machine would say, okay, if you want me to stay, I'll first go to the left and then come back to the right. That way, I have effectively achieved what a stay would do. And therefore, that Turing machine would be enough to simulate this, and you can continue this argument. This one is an extremely simple variation. The need for a stay, not having to move left or right, is fairly realistic requirement, but it hasn't empowered the Turing machine in any way. The left and right moving traditional Turing machine will effectively or very comfortably do that by having to do one more thing. For every stay, there is 2 actions to do. All right, but we're going to see a number of more other variants. I'll call these things variants, where simulations of this type, not necessarily simplistic like this ones, will help us achieve. So the first variation is non-trivial, quite frankly, to say, okay, you had a Turing machine, and our claim in our discussion last time was a Turing machine would do what real computers can do. And then they were given, it has got a tape and a control and a tape head to move around. And we know what computers can do today. And so would it make sense then to say, if I had a Turing machine, but instead of just one tape, it has got multiple of them, would it be a machine then that can do more, can recognize more language than what the traditional single tape Turing machine would do? And I have, from now on, I will be having a few variations we'll discuss like this one. And for every single one of them, I'll get right to, to the case and make the statement and then come back and show how the simulation will be done rather than build up for it. So the result is that this is not going to bring up any new power. Every multi-tape Turing machine has an equivalent single tape Turing machine is the result. And from now on, I will call these variations, I'll give them a name, variation 1, and I'll have a couple other ones, and I'll call them variation 2 and 3. And the corresponding theorems will be named after that. So the book has got its own numbering and things like that, but I wanted to have this correspondence for you clear on these slides. So the proof would then be, and this will be the standard procedure we'll follow now, we've got a statement that talks about equivalence between two machines. There is a question on the chat, on group chat, that says, can you explain what it means for a Turing machine to be robust again? A Turing machine is robust, or generally a computational model is robust, if a change to the definition has not made it have recognized more language. It has become more powerful. For example, this Turing machine has become now multi-tape. Has it become more powerful than a single tape machine? No, then it is robust. That's what I mean by robust. So the theorem is, the result here is what would be important rather than having how, the extra explanation we can give when this is satisfied. So the statement here is multi-tape Turing machine is equivalent to single tape Turing machine. They would recognize exactly the same class of language. And so the proof for this one would be to convert the newcomer, the multi-tape Turing machine, to an equivalent single tape Turing machine. If I have an M like that, can I simulate it with a single tape Turing machine? And simulate means do exactly the same thing. All right, so we're going to do that, and we are going to get a little more sophisticated in how the simulations happen, but the idea of having to simulate for a newly arriving variation of a Turing machine using the standard definition of a Turing machine would be the running theme. And so the idea here would be to say, I will have a Turing machine M, that was the multi-tape one, and I have S, that was the single tape one. Will S be able to do what M was doing in some fashion? And so the M now, as you can see, has multiple tapes, and the single tape Turing machine will kind of put these things together into one. And so the idea, before I go to the details, will be to kind of compress the 3 tapes, or in this particular drawing, I'm showing 3, but the K tapes that the multi-tape Turing machine has, can it be simulated by having one single tape Turing machine that does the same way? And so that's what we're going to be doing. And so in terms of at least lengths of the tape, remember what the tape was signifying in a Turing machine. It's memory, and it is unrestricted, and we have it's unbounded by size, and we have unrestricted access to it. That's what makes a Turing machine. And so when we are putting these K tapes that the original multi-tape Turing machine has by a single one, we still are in the realm of Turing machine, because we have increase the memory or the tape size of the single one to be as many as what the multi-tape one was doing, except that we've put it in a single one. And so we need to, we have that freedom, we have that ability. What we need to do now with the single tape Turing machine is keep track of things. And so one of the things we would want to do is separate. The original one had multiple tapes and multiple tape heads, and therefore it had its own way of knowing where things are and how things are moving. And now we have assembled them in one place. We need to know where the first tape ends and where the second tape begins, and so on. And so for that reason, the single tape Turing machine now needs to have a special symbol as a delimiter to separate these contents. And we're going to use this hash symbol for doing that. That's one. Delineation of tapes is what the single tape simulator will need to have. And the other thing is it will need to know the heads of the different tapes in the original one, in the multi-tape one. And there is a simple solution for this one to say, I've got the symbols, the input alphabets that the multi-tape Turing machine had will be there. I will have them, but I will have twice as many, where I would say, in this particular case, whenever there is the head that I want to show, the single tape machine would have a dot on top of the symbol of the input alphabet to indicate where that one would be. So I have a hash, and the dot together will tell me how far the first tape is, where it begins, where it ends, and where the tape head is for that one. So in this example, for example, the tape head for the first one was on top of a 1, and so the 1 has a dot. The tape head for the middle tape that you see was on the third A, and so the third A has a dot on its end, and so on. So you can see this one. So we have now come up with a way to organize things so that the single tape Turing machine will do the simulation. What I have in this page is the details of it. I have told you how things are set up. So now what one needs to do, and we have gotten a flavor of how Turing machines, when we program them, when we write an informal description for them, would work, is to make sure that every single thing that can happen is being taken care of. And so what the original one was doing, when we want to replace it by what the single tape Turing machine would do, after we have arranged it for this setup, would be to initialize and then go through the steps one by one to make sure that what the multi-tape Turing machine was doing is done by the single tape Turing machine. So I have cut and paste basically, and this is what the book's description has. And then I would like you to have it so that you, when you if you come back and look at these slides later on, you have a complete description, but there is no point for me to actually go through and read them. Basically what we have done now is initialize. The first step is the initialization step, and the input had W1 to Wn, that was the n length input string, and it has now been placed on the single tape Turing machine's tape. It's placed in this fashion to show you exactly where the inputs are, and it is demarcated. The multi-tape one now has got the blank spaces, and the dots are there, so because nothing has happened. This is the formatted tape, and from now on, the other two steps will do what the multi-tape Turing machine would have done, and how the single tape is doing it. And so this is a way for us now, through the single tape Turing machine, to create virtual heads instead of the real ones. And virtual, the notion of virtual, you as 95% of the classes, computer science is a familiar term. You've got virtual machines. So you've got an actual machine, and you've got a box that looks like what the machine is doing, but it is not a real one. So these tape heads that the single tape Turing machine is doing is kind of mimicking what the actual tapes of the multi-tape Turing machines were doing. And so at the end of this one, mathematically speaking, you will be convinced that they are equivalent, because this is how the simulation has happened. So we've taken care of variation 1. And I hope that one was clear. If not, please keep asking me on the group chat. I'll keep an eye. And I'm going to want to go to the next variation, which is conceptually not an entirely new one. We know this notion of non-determinism. And I have, every time I got a chance about it, I have told you, this is one of the places where we have more power added to things in some ways, but not necessarily when we come to certain classes of languages. The power is coming in terms of flexibility, in terms of sometimes convenience to explain. And later on, towards the end of the semester, probably that week or the week before it, we'll talk about complexity results, and you will once again encounter it. So we have encountered non-determinism when we were talking about finite automata. So the basic idea behind this one is, in a computation, there is a possibility of having several possibilities. Just like you have a transition function, you've got one state and then one input is coming. Instead of always going to a particular state, there is a possibility for someone to go to multiple options at the same time in a non-deterministic fashion. It's not very intuitive. That's not how our programs work. When you write things, they are deterministic. That's by nature how they are. But now we have a way. And so that is what we will now see in a Turing machine, if this is going to endow the machine with more power than what a deterministic one would do. So in other words, the transition function now, instead of going from the state and the tape input, that's what the tau is, and going to another state and some change in the tape configuration, and then moving to the left and the right. That's what we had seen before. Now we have the power set in front of it, which means we have 1, 2, 3, 4, many possibilities for going for the same exact situation to something potentially different ones. That's what nondeterminism would mean. So one way, I have told you this one before, to interpret what a non-deterministic computation would be, including a non-deterministic Turing machine, would be to think of it as a tree whose branches correspond to different possibilities. So that transition function that you just saw now, that goes to a power set, could be viewed as having a tree where you have the initial configuration, and then I've got one way, one of the non-deterministic computations would lead me in one of the branches to some state at the end, and then another branch will take me to another one, and the third one, and so on. And these branches could happen at any point during the height of the tree. So that is a very helpful way to interpret how non-deterministic computation would happen. And if one of these branches leads to an accept state, then that non-deterministic computation would accept the input. Otherwise, if there is no place where there is an accept state, it would get to a reject. And I had told you this before, just the fact that we have one branch of computation that we have traced and it led to a reject does not mean the whole thing would reject, because we may have other options for having to determine. So this is what non-determinism is. We haven't said anything other than recapping what non-determinism means, and we saw it in terms of what Turing machines are. And so the big question then is it true, just like it was with finite automata, non-deterministic Turing machines are equivalent in power to Turing machines? And the answer is yes. And this might surprise you. And the first time I heard it, I was surprised. I mean, this Turing machine itself has got unrestricted memory and all of the things that we have said about it. And now, if it in addition can also guess, if it can jump and then have many possibilities, there must be a way for which this one would be able to recognize more language than what the deterministic one would do? And the answer is no, they are equivalent. And it is the proof idea for this one would be a little bit more involved than what we saw in this first variation. We are on variation 2, by the way. And the idea otherwise is the same. Do we have a way to simulate what a non-deterministic Turing machine would do with a deterministic Turing machine? If we can do that, then we say we can do this successfully for anything that has come our way, and therefore we are able to then say the two models or the two machines are equivalent. They would recognize the same class of language. So the idea behind the simulation is to make this deterministic one now kind of exhaustively try all possible branches of the non-deterministic computation and make sure that it will do it. So if it has tried all of them and it arrives at the same conclusion as what the non-deterministic one was doing, then we say the two are equivalent. You may want to go back and look at how we have proved the equivalence between NFAs and DFAs. We tried a little bit different approach there. Here is a brute force approach. We are trying to enumerate all the possibilities here, and the deterministic variant is going to be able to simulate this one successfully. So if D ever finds the accepted state in one of these branches, then D would accept it. Otherwise, this simulation will not terminate, because even though the non-deterministic one could have arrived at a deterministic, an accepted position in one of its computations, we were not able to discover. D was not able to discover it, and so it will fail. So I have the details of this proof coming up. But now that I have told you it's a tree, now that I have told you it's about exploring this tree and finding it, then immediately, I think most of you, you've probably taken an algorithms class, or you're taking Math 216, or you've been exposed to tree exploration or graph exploration. And so there may be something that's already coming to your mind. I need to now know, here I have a conceptual tree that is representing what the non-deterministic machine was doing. I'm going to explore and see if there is a place where there is an accept, and my deterministic machine is now after it. It's going to try to get it. So if I'm going to try to explore a tree, what traversal methods do I have? And I'm not going to probably ask for participation, but one of the things that might come to your mind is to try to do depth first search. And so you've got a tree, you want to go around and find out if there is an accept somewhere. And so you go in a depth first fashion, and then you find a reject. And so you say, okay, this is not going to be accepted. And that will be a wrong conclusion to make, because there could have been an accept somewhere else. You just didn't dive to the right place. And this one would just immediately tell you depth first search is not a good one, because you could miss, whereas breadth first search would be the right choice here, because at every level of when you go, you explore everything, and the first time you get an accept, you will take it, because that's what the simulator would now do. And so the right choice here will be a breadth first search in this exploration of the non-deterministic tree. So this is the proof idea. Look for a place where the non-deterministic one was doing, get the accept place if you discover it. If not, keep looking for it. When you discover it, you will report it, is what the deterministic Turing machine simulator would do, and the right tree exploration for it will be a breadth first search. So what I'm going to be telling you from now on will be how to go ahead and apply this idea, this basic idea. And I'm going to use a couple of slides for doing it. We're going to take advantage of a knowledge we just found now. We had in variation 1 found out that adding more tapes to a Turing machine is not going to add power. They are equivalent. But we will find it very convenient for us now to do this simulation with this deterministic D, our tree, or our Turing machine will do what the non-deterministic one was going to do, but it's busy. This deterministic Turing machine is now busy having to worry about many things, and therefore it would help us if we make it have multiple tapes and multiple heads, because now we can make them work on different pieces. It's more like a good division of task or a way of conquering this fairly complex thing that the deterministic Turing machine has to take care of. And for that reason, we are going to have it have multiple tapes, and they will have different responsibilities. But this is not going to make us go the wrong way, because we know they are equivalent. And so whatever it is that we argue now for this multi-tape deterministic Turing machine D as a simulator for our non-deterministic one, if we successfully finish this story, we are going to declare victory and then say, okay, these two models are equivalent, non-deterministic Turing machine and deterministic Turing machine, because the way I have constructed the simulator, my deterministic Turing machine has got multiple tapes, and it did what the non-deterministic one was doing, and therefore they were equivalent. But then also I know that adding multiple tapes is not going to make it any more powerful, and therefore this is equivalent to a single tape Turing machine. Will be the end of the story. Okay, so what are the 3 tapes that I would need? The first tape with my simulator, with my deterministic Turing machine, will be containing the input string, and it's not going to change it, it's not going to alter it. The second tape is going to maintain a copy of n's tape on some branch of its ND computation. Remember what we are trying to do. We are looking at the non-deterministic computation of the original machine, the non-deterministic one, so it's a tree and it has got multiple branches. We want to keep track of one of the branches, and that's what tape 2 is going. It is simulating it for one branch. And the third tape is going to keep track of the location in n's computation tree, because the simulation tape is having to do with one branch, and so it is taking care of that computation that has happened there. But I've got multiple branches, that's why it becomes a tree. And so I need to know where in the original non-deterministic machine I am for this tracking, and therefore I need a way to come up with a way to track, and that's what this third one would do. And we'll call that one an address space. So we've got the input, we've got a simulation tape, and we've got a mechanism for which we have found a way to know where in the non-deterministic Turing machine we are. And now it looks like a number. You will understand why it is numbered in this fashion when I continue explaining. All right, so what we are going to be doing now is look at the third tape, the one that traces the location in the original non-deterministic machine. And we will begin with working with the numbers. So we're going to consider how data is represented on this tape 3. And if we go back to the non-deterministic machine, it will have at most B children. And so that's the bound we have. And so this will be the size of the largest possible of choices in n's transition function. So if you remember how I defined the transition function for a non-deterministic Turing machine, it had states, it has a tape alphabet, and it was going to another tape, some changes to the tape, and then left or right, but then it was in a power set. And so that power set could be of size 1, 2, 3, and so on. It could go on like that. So for one particular transition function, for one combination of things, I could have 2 things to choose, 3 things to choose, just one thing. And so there will be different ways. And so I'll call the maximum possible choice I have anywhere in that computation. That's what B is showing you. Okay, so we've got a number that could be a bound. And we're going to be assigning an address now using a special mechanism for us, a special way of organizing things, and it will be a string. And so it will be based on numbers, but it will be a string, and that string is over these alphabets 1, 2, up to B, where B is the maximum branch, the widest place where that tree is forking off. So for example, if we assign the address 231 to a node, we will give this number to the one we arrived by starting at the root of the non-deterministic tree. That's the initial configuration. And then going to its second child, it has got B children potentially. It could have fewer. So going to the second child, and from that second child, going to the third child of that, and then finally going to the first child. That's what the 231 is. So from the root, I'm picking the second child. Of the second child, I'm picking the third child. And of the third child, I'm picking the first child. So I have a way to address it in the original non-deterministic computation. Here is the address. That's what this address is showing. And so I'll go on in this fashion. I have a way to address it. I have a way to keep track of which branch I'm talking about. I have everything I need in this machine now. So each symbol in this string now will tell us which choice to make next when simulating a step in one branch of the NS computation. Sometimes this symbol may not correspond to an actual choice if there were too few choices available for that configuration. In that case, the address is going to be just invalid and doesn't correspond to any node. So step 3, the way I have explained it now, will contain a string over this alphabet that I defined over numbers, and it represents the branch of the computation of the non-deterministic Turing machine, starting from the root to the node that's being addressed by the string, unless the address is invalid. And the empty string will now show us the root of the tree. So I have now, probably if you have been following me, found a way to organize things so that my deterministic Turing machine will mimic, or we will try to find what the non-deterministic one would do, at least the organization of the data. So the rest of it now will be to see how you would go around and do what the non-deterministic Turing machine one was doing. This one is, as you can imagine now, not going to be too helpful to go line by line, but the idea is to implement what I told you now with what the non-deterministic Turing machine one was doing by having to do the deterministic Turing machine that has got these 3 tapes and a way of organizing things to follow along. And the rest of this discussion tells you how that one would do. When this one is fully described, and when you get to very closely examine it, some of you might have already done, what you will finish, or what you will conclude, is that this is the end of the proof for the statement we have made. Non-deterministic Turing machines are equivalent to deterministic Turing machines. That's why actually when we were informally describing Turing machines in the very beginning on Monday, we would never even care about calling them deterministic or non-deterministic, because it doesn't make a difference. And the discussion was easier when we formulated the transition function as if it was a deterministic one. And at that point, you might remember I told you it looks like a deterministic one, but it won't make a difference if it was non-deterministic. All right, we did 2, and we have one more to do, one other variation. And this variation looks cool because it's got a printer attached to it. So what if my Turing machine now has got a printer that would print out things and I would enumerate them. When I had these class diagrams drawn last time, I told you Turing recognizable machines are also called recursively enumerable. And this is where that motivation for that one would come. So very loosely defined, an enumerator is a Turing machine that has got a printer attached to it. And so the Turing machine can use that printer as an output device to print strings. And every time the Turing machine wants to add a string to the list, it just sends it to the printer. So it will be able to enumerate all the strings that it will do. So this is a definition for an enumerator on how things look like when they are set up. So an enumerator now starts with the blank input on its work tape. This is the tape that is attached to the Turing machine. And if the enumerator doesn't hold, it may just print an infinite list of strings. And so the language that is enumerated by this enumerator E is the collection of all the strings that it eventually prints out. So whatever this printer is able to spit out at the end will be called the language. The set of the language consisting of all of these strings is called the language enumerated by E. And E may generate the strings of the language in any order. It doesn't have to be in any particular one. Sometimes we may even repeat, then the language doesn't change. So the list of strings is what would determine what the language is. Some of the strings may repeat more than once. Some of them, they may not have any order of anything that we can explain, but that collection is called the language enumerated by that language. And so the statement, just like what we had the statements on the first two variations. First variation was a multi-tape Turing machine is equivalent to a single tape Turing machine. Second variation was non-deterministic Turing machine is equivalent to a deterministic Turing machine. The third one that we are looking at now is a language that is recognizable, Turing recognizable, is called Turing recognizable if and only if some enumerator enumerates it. In other words, an enumerator is equivalent to a Turing machine is what this statement is saying. And so the proof would then be, because it's if and only if, will be to show if I'm giving you an enumerator, can you give me a Turing machine that recognizes it? And the other direction would be, if I give you a Turing machine that recognizes a language, can you give me an enumerator that would do it? So let's do the first one. If we're given an enumerator, can we have a Turing machine that would recognize that language? And we'll call that language A. Let me actually see what time I have. It's almost 11. I know some of you may need to go to a class. I'm going to be quick on this one, just show you this slide and then go. Is there anybody who has got any question before I continue with this? If you need to leave immediately for a class, that's fine, but I don't know if I should say fortunately, but this is one of the things that happens because we are online. You could stick around with me for a minute or two before you go to your next slide. I just want to finish off this discussion, but anybody else got any question? All right, so if we have a Turing machine that would recognize given an enumerator would do run it every time this enumerator outputs a string, we compare it against our input. If it is accepted, if it appears in the output, we'll accept it. If not, we don't. And that will be how the Turing machine would recognize this language. It would accept it if there's one. The other direction is not all that different, except that we have now to worry about each one of these things one at a time and make sure that we have an enumerator that would find this one out. The only detail I want you to pay attention here is that it might, infinitely many times this machine is running from the beginning of the string for each repetition of the state. That's what detail I want you to see when you get a chance to look at this slide again. And that's probably the only one. Otherwise, the two sides are equivalent, will be the end of the story. All right, these were the three things I wanted to discuss, and I will next time talk about another equivalence, and I know 4 or 5 of you at least have to leave. I'll pick up on this one next time, and it's not going to hurt us. But I have left them the notes of what I wanted to do. It has to do with one of the things I really care about, if giving a formal definition for what an algorithm is. And that will be what we'll be talking about next time. Let me stop for now here. This is the last slide, and I'll pick up the discussion from here. And if you're following along in the book, this will be section 3.3, and that will pick up. Otherwise, the discussion for next week will be around undecidability. All right, was good seeing you. Let me know if you have any questions, and otherwise we'll stop here. See you next time.